Okay, our next speaker is Lukas, Automatic Multi-Parameter Design Optimization for Superconducting Devices.
Hi, everyone. Today, I'd like to present to you our most recent work on a Q design optimizer, which is an automatic multi-parameter design optimization for superconducting devices. And this work was not just done by me, but by our amazing team at Chalmers University under the supervision of Simone Gasparetti. And the problem that we like to address is very familiar to you, and the people who've stayed since 11:30 here in the session, they've seen this workflow now multiple times, but let me reiterate it once more for those who came late. When we design our superconducting circuit, we maybe start with a Hamiltonian, have some parameters in mind, that we then translate into a physical 2D layout. We route some wires from left to right, and then is the moment when we simulate the structure. People use different software, but here we especially refer to ANSYS HFSS, and obtain parameters for an eigenfrequency, some coupling from an EPR analysis, and we compare the target value with the just obtained current parameter. And then based on that, we decide, are we satisfied, or do we move on and reiterate, check the Hamiltonian, update the design, and so on and so forth. And for a very long time, this job was done manually supervised. There was a PhD student, most often sitting in the lab for many hours and running through this loop until the PI and the PhD student were happy. And now many other packages that we've also discussed here in the session today address this point in very different ways. But yeah, most often we would make small changes here to the capacitance island, also to make a single qubit example like the one here presented with 5 parameters work. But it's manual and time consuming in most cases. And what I'd like to show you today is our approach and our solution towards this optimization problem, which is slightly different to the squat approach that we've seen before. Now, the first thing that we need to do when we start with the optimization is we need to parameterize our circuit appropriately to address the problem. Now, when we think about a single qubit example, then there are typically 5 parameters that we have in mind: the qubit frequency, the qubit anharmonicity, the chi between qubit and resonator, and the resonator frequency, and the kappa, which is the coupling to the feed line. To those parameters, we will refer to optimization or target parameters Q. Those target parameters have a physical link, physical representation. For example, they can be controlled by the capacitor widths, by the junction EJ, by the coupling separation if there's coupling ports to the qubit, the resonator length, or the coupling lengths here. And this is something that we choose also in a manual approach to be the tuning variable to adjust the design. And we refer to these design variables as V. Now, the important part in our optimizer, and this is something that I want to highlight here on slide 4 already, is the physical relation. Yeah? And that is the key component here, where we bake into the optimizer, contained in an object that we call opt target, the physical relation that basically has an approximate physical model connecting the design variable to the target parameter. And for the frequency of a resonator, we have this inverse relation that can be implemented. But of course, for many other parameters that we find in our circuits, we can write a similar approximate physical model and input this into the optimizer. Now, when we step through the optimizer, we start all the way at the end there with a detailed numerical model. And this can be an HFSS eigenmode simulation, it can be a capacitance simulation, it can be an EPR analysis. These are the 3 simulation and analysis types that we've implemented right now, but we're working on several more. But what they give us are the optimization targets Q, which we like to compare. And we do this comparison here in this example, and I stick with the resonator frequency. So, for example, the simulation outputted a resonance frequency of 6.5 gigahertz, and we compare to the target and see 7 gigahertz. No, there's a mismatch. We continue the optimization. Now, the question is, how do I need to change the design variable in order to get very close to the target? And this is done during a step which is the prediction based on the physical relation. Yeah? Implemented by this equation, what it means concretely is that we have our updated frequency that we want to aim for. We have a current frequency that we've just computed, and we know what the current length of the resonator was, and then all we do now is we put this equation to a cost function, minimize for the design variable here, the resonator length that gives the most accurate estimate for this target resonator frequency. And this step of optimization, this step of simulation and prediction takes maybe a couple of iterations. So we run through this optimization loop m times, but at some point we're satisfied, we reach a convergence, and this is when we move on and validate our results. We basically check that the numbers that we've obtained make sense, and then we populate our design database with the design variables that we've obtained from this optimization. Now, this is the algorithm, and now for the rest of the time, I like to show you a couple of examples that we've implemented and that you can also find and directly play with in our Python package that we've prepared for you. So here in this simple example number one, a qubit resonator system, we have the structure with the 5 parameters that I basically presented to you before. And now in the 5 panels, now we see the target parameter, the resonance frequency, and so on and so forth, versus the iteration. And the iteration is the number of optimization steps that we run here. And what we can see in this example is essentially that for within about 6 iterations or so, the design has reached convergence fairly well, and then depending on how much money you spend on your lab computer, this optimization takes maybe 10 minutes or 1 hour. I seem to have a slightly cheaper PC, but my colleagues run the simulation in 10 minutes, so it really depends on the hardware configuration of your computer. But what I really want to stress here is that we obtain a fast, nearly or almost everywhere monotonic convergence within 6 iterations based on this physical model. Now, I'd like to discuss this physical model and the relevance of it a little bit further. In principle, it is very important to write out a design that separates the physical quantities in the system clearly. Here in this example, we've chosen 2 different physical relations for the estimation of chi. And you can see that in both cases, the convergence works surprisingly well. Within 6 iterations or so, we have the simulation and this optimization close to our target. And this is to say that you can be somewhat sloppy with the preparation of this physical relation as long as it indicates the right trend. And now there are more examples, but the story repeats. So here's a 2-qubit example, and it converges. We can also do capacitance simulations, and we have 2 examples prepared here. One where we study the mode decay into a charge line. We prepare the T1 limit as our target parameter, and we adjust the distance to this coupling port in such a way that we reach a T1 limit of 20 milliseconds. Now here, sometimes you're interested in a certain capacitance value between 2 structures, and that works in a similar way. Now, maybe interesting, but also discussed today, is the comparison between simulation and measured values. In general, it is very important, as we've learned in several talks, that the convergence is good, and this sets the accuracy of this optimizer. But even here, for this kappa estimate, we obtain generally a good comparison between the simulated and the measured kappa. Now let me summarize. So we've prepared this design optimizer that runs through this loop, but for you, while you have a coffee, and spits out the optimized design. Very important is to include the physical relation. And this model is general enough such that you can also include or use this idea of the physical relations in any of your design flows, whether you use ANSYS and Kiskin metal or not. Check out the code. It's on PIP, and we have a webinar to show you more about this optimizer. Thank you.
Are there any questions? Okay, I had a quick question. I think this was maybe slide 6 or 7, where you showed this example of a resonator and qubit. Yeah, so the kappa plot, as you're increasing the iteration, it seems to stay fairly noisy. Do you know why that is?
Yes. In fact, this is the note I did not read out. It's at the bottom of the slide, and it relates to the fact that the imaginary part of the eigenmode does not converge super well. And if anyone has a good idea on how to fix these Q mode simulations in ANSYS HFSS, please talk to me, because that's something we're actually struggling with. But we have an alternative which is based on the kappa estimate, and that I've shown you works surprisingly well. Thank you.
Okay, thank you. Any other questions? If not, let's thank the speaker.